In this presentation, I am going to explain stator frequency control of induction motor. The torque and the speed of an induction motor can be controlled by changing the supply frequency. As you are aware, synchronous speed ns equal to 120 f by p. By changing the frequency, the synchronous speed can be changed. Therefore, if the voltage is maintained fixed at its rated voltage while reducing the frequency below the rated value, then flux will be increasing. As you know that the voltage per phase can be equated to 4.445 F T phase into kW. kW is the winding factor, turns per phase T phase, flux per pole, and the flux per pole equal to voltage divided by 4.44 F into T phase into kW, in which 4.44 T phase and kW is a constant. Therefore, the flux is equal to a voltage V divided by constant K into frequency, or flux is inversely proportional to the frequency. Therefore, as supply frequency reduces, flux will be increasing. Thus, the frequency F reduces, then for a given stator voltage, flux increases. This will cause saturation of the air gap flux. Now, if you are keeping the voltage constant and if you are reducing the frequency, then flux will be increasing. That goes into saturation, and the motor parameters would not be valid in determining the torque and speed characteristics. The motor parameters value will be changing from the rated values. Therefore, at low frequency, the reactance decreases, because as flux increases, as the frequency reduces, flux increases. And at low frequency, as frequency reduces, reactance decreases, because it is equal to 2 pi f into L. Therefore, as frequency reduces, reactance reduces. As reactance reduces, the motor current increases, and that will cause more losses, and that cause efficiency gets reduces. Therefore, reducing the frequency, keeping the voltage constant will cause two effects. One thing is that will go into saturation and the parameters value will be changing. Second is that the current will be increasing and the losses will be increasing, and the efficiency gets reduced. This is what happens when voltage you are keeping constant and you are reducing the frequency. Even though you can control the speed, these two effects will be there. Continuing stator frequency control, the synchronous speed corresponding to the rated frequency is called the base speed, that is omega b. For speed control, below the base speed, while frequency is reduced, the voltage is also reduced in proportion to, so that V by F ratio is constant. That is the normal method. Therefore, as frequency reduces, the voltage also reducing, keeping V by F equal to constant. The ratio is kept constant. Therefore, flux remains constant. Therefore, in constant V by F control, the flux remains constant at its rated value. That's called the V by F control. That is done for the speed less than the base speed. We are controlling the speed of the induction motor less than the base speed by V by F control, or by reducing. When we are reduce the frequency, speed reduces. At the same time, you are reducing the voltage and keeping V by F equal to constant. And in this, during this control, the maximum torque remains same. That is very clear from the graph. That's maximum torque is remains same. If you are reducing the frequency, maximum torque is remains same. And this type of control is used for the speed control of induction motor less than the base speed. Continuing stator frequency control, the synchronous speed corresponding to the rated frequency is called base speed. That is already told, that is equal to omega b, this base speed. the synchronous speed at any other frequency that is represented as equal to a constant k times omega b. And the slip is given by, as you know that one, omega s minus omega m divided by omega s. Then omega is already k times omega b. For k times omega b minus omega m divided by k times omega b. That is the slip. And the torque can be written as 3 by k omega s into kv whole squared rs dash divided by slip s divided by k omega b into rs plus rr dash divided by s whole square plus kxs plus kx r dash whole square. That is the torque equation, where V is the rated voltage and Xs and Xr dash are the stator and rotor reactance at rated frequency. Maximum torque at the rated frequency is Tmax is given by 3 by 2 omega s into V square divided by Rr dash plus root of Rr dash plus Xs plus Xr dash whole square. Or if Rs is neglected, maximum torque is given by 3 by 2 omega s into V square divided by Xs plus Xr dash. For the maximum torque at reduced frequency is given by 3 by 2 omega s into V square divided by Xs plus Xr dash whole square. That is the stator frequency control. Continuing stator frequency control. As we have already seen in the previous slide, for the speed control below the base speed, the maximum torque remains constant if you are keeping V by F ratio is constant. Therefore, if you are controlling the speed of the motor less than the base speed, we are using V by F control and the maximum torque is constant. That is, this region maximum torque is constant less than the base speed. Now, if you control the speed of the motor more than the base speed, then you are doing what? You are increasing the frequency. Therefore, as you increase the frequency, that for the speed control above the base speed, the voltage is kept constant at its rated value, because you cannot increase the voltage more than its rated value. Therefore, you are keeping the voltage at rated value while increasing the frequency above the rated frequency. Now, if the frequency is increasing, as that previous equation we have seen, as frequency is increasing, flux is reducing. As flux reduces, torque gets reduced. Therefore, since V by F ratio is decreasing, in this case V by F ratio is decreasing because voltage, you are the rated voltage, we are not increasing above rated voltage. For V by F ratio decreases and then flux decreases, and the maximum torque is given by that equation, which means that the maximum torque decreases by a factor k square. You can see that from this equation, the maximum torque decreases by a factor k square, where k is greater than 1. That is, maximum torque is inversely proportional to the square of the frequency, similar to the behavior of a DC series motor. That is what is happening if you are increasing the frequency. Therefore, in this mode of control, the motor is set to be operated in field weakening mode. For the control of the induction motor for a frequency above the rated frequency, the mode of operation we call it as field weakening mode. In that case, this is the range in which we can see that one torque is reducing. Torque is inversely proportional to the square of the frequency. As the frequency increases, the maximum torque available gets reduced. That is what's called the field weakening mode. That is what is happening when frequency increases. The voltage at variable frequency can be obtained by a three-phase cycloconverter or three-phase voltage source or current source inverter. The cycloconverter is used in very large power application like locomotives and cement mills, where the frequency requirement is either 1/2 or 1/3 of the frequency. But normal application for the induction motor control will be using PWM, sine PWM techniques to control the voltage and frequency. That we'll be seeing in the Next slide. Next, we are going to explain sine PWM inverter fed induction motor for V by F control of induction motor. Therefore, we are considering a inverter, a three-phase inverter. In each leg, there are two switches, and here DC bus, a voltage VDC supplied, and that is connected to the output of this one. Each leg, middle of the leg is connected to the stator of induction motor. Now, to generate the switching signals, what as already I have explained, there are two control signals. One we call it as modulating signal, low frequency modulating signal. That's a sinusoidal signal that is compared with a triangular signal, that is a high frequency triangular signal using a comparator, and that comparator output that is given to one of these switches in a leg, top switch, and the bottom switch will be the complement of that one. Therefore, like that one, each switches in each phases are given, is generated by comparing respective phase voltages and high frequency triangular signals. Now let us see how the voltage can be varied. As I already explained in the previous slides, how you can vary the fundamental voltage applied to the stator, similar voltage as well as the frequency. And here, as I already explained here, there is a one index, what we call it as modulation index, amplitude modulation index. That is the maximum value of the modulating signal divided by the maximum value of this triangular signal. That ratio we call it as modulation index, MA. Maximum value can have this MA equal to 1. Normally that will be working in the range of 0.8, 0.9 like that one. And similarly, one more parameter is called the frequency modulation. That is the ratio of the high frequency triangular divided by the frequency of the modulating signal. That ratio we call it as modulation in frequency modulation index, MF. Now, how the output voltage is related to these parameters. The output voltage, the peak of the fundamental output voltage, that is VL1, that is equal to MA, amplitude modulation index, into DC bus voltage VDC. This is the maximum magnitude. And maximum magnitude of MA can be 1, or it can be less than 1, maybe 0.8 or 0.9 or 0.7 like that one. Therefore, the RMS value of the output voltage is given by MA VDC divided by root 2, or that is equal to 0.707 MA times VDC. Therefore, this RMS value of the voltage that is applied to the stator can be varied by varying the MA or amplitude modulation index. That can be varied by the magnitude of modulating signal, because normally the carrier signal is kept constant. Both frequency and magnitude of carrier signal is not disturbed. What we are changing is the magnitude and frequency of the modulating signal, low frequency sinusoidal signal. Therefore, by varying the magnitude of the modulating signal, you can vary the magnitude MA. Thereby, you can vary the RMS value of the fundamental output voltage. Now, let us see how frequency can be changed. Output frequency, fundamental frequency is same as the frequency of the modulating signal, or that modulating signal, or the frequency can be changed by changing MF, or that ratio MF. Therefore, by changing the frequency of the modulating signal, you can vary the output frequency. By changing the magnitude of the modulating signal, you can vary the magnitude of the output voltage. There, you can vary both voltage and frequency of the output of this inverter that is applied to the stator of the induction motor. This is way how a sine PWM can generate a variable output voltage with a variable frequency by changing MA and MF. As a conclusion to sine PWM inverter for induction motor drive for V by F control, in sine PWM inverter, output voltage and output frequency can be controlled within the inverter by varying the amplitude modulation index MA and frequency modulation index MF. The maximum value of the fundamental voltage is given by MA into VDC, or RMS value is given by 0.707 MA into VDC. Fundamental frequency of the inverter output voltage is the modulating signal frequency, or frequency of the lower frequency. There, by using sine PWM techniques, you can get a variable output voltage with a variable frequency for controlling V by F control for an induction motor.